Alright everyone, welcome back. We are again talking about centripetal force, but this time in the vertical direction. I do believe this is the hardest part of the unit, so here we go. Alright, so some notes to take that will be very helpful for the coming problems. Okay, so when objects are moving in a circular motion in the y direction vertically, multiple forces may be acting either away or towards the circle. All forces that act directly toward or away from the circle will affect the centripetal acceleration and must be accounted for. When solving for acceleration or force, we will take the downward direction to be negative and the upward direction to be positive. Okay, so this first example here, we have a car going up a ramp, right? Going up this way, let's say. We can see that there's a force of gravity going down towards the center of the circle, and there's a force normal going up away from the circle. And we should know that the acceleration centripetal is also always going to be going towards the circle, so that way. So this is how we're going to set it up. We're going to do all of the forces in the y direction is going to be equal to mass times acceleration centripetal. Okay, since it's moving with a constant speed, uniform circular motion, the only acceleration is this centripetal acceleration. So we have force normal going up, that's why it's positive. Force of gravity going down, that's why it's negative. And we have this mv squared over r, and that is negative because, as we can see, the acceleration is going down. Okay, same thing over here. This car is going through a dip. We have normal force, which is positive, going towards the center of the circle. Force of gravity going away, so that's going to be negative, and it's going down. And acceleration is pointed towards the center of the circle, so that's positive. So positive, positive, negative. Okay, and this bucket it seems like it's going around in a circle like this. Again, force of tension is going towards the circle, and acceleration is going towards the center of the circle. And they're both going up, so they're both positive, while this force of gravity is going down negative. Okay, I hope that makes sense. As we do more of the example problems, it'll make more sense. So if you're troubled at all, we'll just do those. Okay, first conceptual example, number 18. A car driving up a hill with constant speed. When the car drives past the top of the hill, what will happen to the amount of contact it has with the ground? And again, you can try to pause, if you want to pause it, feel free to do so and everything like that. Okay, so one thing we want to, I guess I just want to kind of show this conceptually. As this car is going up, when it reaches this top part, if it's going really, really, really fast, it's actually just going to like fly off this little hill, okay? And what that's telling us is as it goes up this hill, it's kind of going to be losing a little bit of contact with the ground. Meaning it won't have as much contact with the ground, and that means that even though the force of gravity might be a lot, the weight of the car might be a lot, the normal force might just be very little. Okay, and that should kind of make sense if you've ever been on these hilly rides. When you go on top of the hill as you're driving fast, you almost feel your body lifting off the ground. So you won't have as much contact with the ground, meaning your normal force will decrease. Okay, moving on. A car driving down a hill with constant speed. When the car drives down through the dip, what will happen to the normal force the car and the passenger car experiences? Okay, so now we're going kind of opposite. We're going down inside of a dip. And we know the force of gravity doesn't change. Your weight, the weight of the car, it doesn't really change. However, what happens to the normal force? Again, you pause it if you like. But what's going to happen is the normal force is going to increase. And you could think about this car going down, and as it's going around this curve, it's almost like the car is getting squished with the concrete, squished against the ground. And that means since it has more contact with the ground, the normal force is going to increase. Okay, hope that makes sense. And we'll be showing mathematical proofs of this later on. Okay, so a little example video. Hope you guys look at it. Now let's look at this. When the car goes through the loop, so that was a video of a car going through a loop-de-loop. At what point is it going to have the least amount of normal force with the pavement? At the top, on the sides, at the bottom, on the way up, at the bottom, on the way down. Okay. So this car is going to be going very, very fast, right? And what's going to happen is, as it goes fast, at the very, very top, if it's not going fast enough, it's just going to fall. This should also tell us that if it is able to go through at the very, very top, it almost wants to fall down at the top, meaning that there won't be as much normal force. There won't be that much contact at the very top. Okay, so that's going to show us that the normal force, since there won't be that much contact at the top, because gravity's trying to pull it down, is going to have the least amount of normal force. Okay, moving on. When the car goes through the loop-de-loop, at what point is it going to have the most amount of normal force with the pavement? At the top, on the sides, at the bottom on the way up, at the bottom on the way down. So we just said at the top it has the least. So it's not going to be that. It's not going to be the sides. It says at the bottom on the way up and at the bottom on the way down. So one thing that we should know is, as this car is going up, right, from the runway, it just has a normal force. So there's going to be a force of gravity, and the normal force is going to be the same as that force of gravity. However, on the way down, it's going to be a little bit different. When it's coming down this ramp, again, it's almost like it's going to be getting squished, and so the weight's going to be the same force of gravity, but the normal force will be so much more because of that getting squished. So it'll be a lot more on the way down. Hope that makes sense. Moving on. Okay, so let's do some mathematical problems. Sometimes this helps us to make it more sense. A car with a mass of 720 kilograms goes over a hill at 12 meters per second. The top of the hill has a radius of 70 meters. I know it's hard to imagine a hill having a radius, but anything with a curvature has a certain amount of a radius. Alright, draw a free body diagram of the car at the top of the hill. Okay, so what are we going to have? We're going to have force of gravity going down, and there's going to be a normal force going up like that. Okay, so it should look something like that. And the normal force should be less, because like we said, as this car is going up the hill, as it's reaching the top, it's losing contact with the ground. If it went really, really fast, it'd fly off the ground and it wouldn't have any contact with the ground. Okay. Okay, B. What is the normal force of the car? Okay, so now that we're dealing with the vertical direction, let's kind of look at how we're going to solve this. So we're doing the sum of all forces in the y is equal to the mass times acceleration. Remember, everything is moving with uniform circular motion, so the only acceleration is centripetal. So let's see everything we have in the y direction. We have force normal, which is going up, force of gravity, which is going down, and the acceleration centripetal, the acceleration is going to be pointing towards the center of the circle. Centripetal meaning center seeking. So that's going to be a negative mv squared over r. Okay, so let's plug in things that we know. Force of gravity is going to be 720 times 10, 7,200. And this is going to be equal to negative 720 v squared, which is 12 squared, divided by the radius, which is 70. Okay, let's try to simplify this. Force normal minus 7,200 is equal to, let me put this all into my calculator, 12 squared times 720 divided by 70, and it's all negative. Okay, negative 1,481.14. Now I'm going to bring the 7,200 to the other side, which is positive. And the 7,200 minus 1481.14, and I get 5,718.86 newtons. Okay. Okay. Part C. If the car went fast in 12 meters per second, what would the normal force increase, decrease, or stay the same? So like I said, as it's going faster and faster, it's going to be losing more and more contact with the ground. And if it goes too fast, it won't even have contact with the ground. It will just kind of fly off this mountain or hill. So what's happening is going to be decreasing. Okay, let's look at this. Example number 16. A car with a mass of 600 kilograms goes down a dip in the road at 10 meters per second. The bottom of the dip has a radius of 80 meters. Draw a free body diagram of the car at the bottom of the dip. Okay, so we know this car is going to have a certain amount of weight. That's the force of gravity. And it's going to have a certain amount of contact. That's going to be the normal force. Okay, and it should be more than the force of gravity because, like we mentioned, as it's going down this ramp, it's going to be kind of getting like squeezed with the concrete. Okay, so it should look something like that. B, what is the normal force of the car at the bottom of the dip? So again, this is in the y direction, so we're just looking at everything in the y. Sum of all force in the y is equal to mass times acceleration centripetal. We have force normal going up, force of gravity going down, and we have acceleration centripetal, which is pointed towards the center, which is positive. mv squared divided by r. Okay. Fn minus force of gravity, 600 times 10, is equal to 600 v squared, which is 10 meters per second, 10 squared, or 100, divided by r is 80. Okay, so let's simplify this a bit. Force of gravity is 6,000. And now let me simplify this. 10 squared times 600 divided by 80. And that's 750. Okay, so now I know force normal is going to be, I'm going to bring this to the other side, 6,750 newtons. Okay, and we can see it is more than force of gravity. It's kind of getting squished. Okay, so part C. If the car went faster than 10 meters per second, would the normal force increase, decrease, or stay the same? And like I was mentioning, the faster this is going, when it reaches the bottom, it's going to squeeze more and more with the bottom of it. So more squeeze, more contact, more normal force. Okay, it'll increase. Okay, moving on. Okay, conceptual example number 22. When the car goes through the loop-de-loop at the very top, which way is the normal force pointing? Alright, so let's look at this. So a lot of times people think, oh, okay, when it's at the top, we have force of gravity going up, and then force normal going up, force of gravity going down, force normal going up. But no, that would not be the case. So if we see that the ground that it's in contact with is right here. So that means, yes, we have force of gravity going down, but the contact force is also pointed downwards. Okay, so it's going to be down. Okay, moving on. Someone at the circus rides a motorcycle through a loop-de-loop that has a radius of 15 meters. If the person and the motorcycle have a mass of 300 kilograms and rides the loop-de-loop with a constant speed of 20 meters per second, what normal force does the person experience at the top of the loop? Okay, so looking at the free body diagram again at the top, we have a force of gravity and we have a normal force. I don't know if it's more or less until I do the calculations, but I'm just drawing it both down. Okay, so part A. Sum of all force in the y is equal to mass times acceleration centripetal. So we have force normal going down, force of gravity going down, and we have centripetal force going down. Okay, everything is pointed downwards. What are we looking for? Normal force. Okay, great. Force of gravity is 300 times 10, and it's going to be equal to negative 300 v squared, which is 20 squared, divided by the radius, which is 15. Okay, let's simplify it. Okay, so let's figure this out. The normal force is going to be minus 3,000, and it's going to be equal to, put in my calculator, 20 squared times 300 divided by 15. And that's going to give us 8,000, or negative 8,000. Put this in our calculator, bring this over to the other side, and it's going to be equal to negative 5,000 newtons. Okay? If you want to put 5,000, it's fine, but yes, it is pointing downward, so it's going to be negative 5,000 newtons. Part B, does the normal force increase, decrease, or stay the same if the person went faster? So we should know if the person went faster, that means there's more contact with the ground. More contact means more normal force, so it would increase. Okay, so someone at the circus rides a motorcycle through the loop-de-loop that has a radius of 15 meters. If the person in the motorcycle has a mass of 300 kilograms and rides the loop-de-loop with a constant speed of 20 meters per second, what normal force does the person experience at the bottom of the loop on the way down? Okay, so now we're not looking at the top anymore. We are looking at the bottom. And we should know as this is going towards the bottom, it's going to be kind of squishing the bottom. So that means even though the force of gravity is going to be the same, the normal force, since it's getting squished, should be more. Okay, so doing the same thing, sum of all force in the y, part A, is equal to mass times acceleration, centripetal. Force normal is up, force of gravity is down, acceleration centripetal is up. Alright, so let's plug some things in. Force normal is what we're looking for. Force of gravity is 300 times 10. It's going to be 300 v squared, which is 20 squared, divided by r, which is 15. So we just kind of just did this already, but some things are a little bit different. We have 3,000, and I know from last time that was negative 8,000. This time it's not a negative, it's a positive, so I know that this is just going to be 8,000. Bring this to the other side, and I see the force normal is going to be equal to 11,000 newtons. Okay. Does the normal force increase, decrease, or stay the same if the person went faster? By now we should know that it is going to be increasing, okay? More contact with the ground. Okay, I believe this is the last one, and then we're going to start talking about something pretty cool next time. Okay, so a bucket has a mass of 1.2 kilograms, is attached to a string that is 0.7 meters long. It swings in a vertical counterclockwise circle. Draw a free body diagram of the bucket when it is at the bottom of the circle. Okay, so we have it over here. We have force of gravity going down, and we have force of tension, the tension of the string holding it up. Okay, so it should look something like that. If the bucket is swinging with a speed of 5 meters per second, what is the force of tension at the bottom? Okay, so part B, sum of all force in the y is equal to mass times acceleration centripetal. We have force of tension going up, force of gravity going down, and acceleration centripetal going up as well. Okay, force of tension minus force of gravity, 1.2 times 10, is going to be equal to 1.2 v squared, which is 5 squared, divided by the radius, which is the length of the string, 0.7. Alright, so let's simplify this. Minus 12 is equal to 5 squared times 1.2 divided by 0.7, and we get 42.86. Now I know force of tension is going to be equal to that, plus 12, and we get 54.86 newtons. Alright, part C. Does the force of tension increase, decrease, or stay the same if the bucket was swung faster? So, anyway, by now we should know that the faster that this is spinning, that means there's going to be more and more tension holding it together, making sure it doesn't fly out of there. So it is going to be increasing. Alright guys, so it looks like we have one more question. A bucket has a mass of, a very similar question. A mass of 1.2 kilograms is attached to a string that is 0.7 meters long. It swings in a vertical circle counterclockwise. Draw a free body diagram of the bucket when it's at the top of the circle. Okay, so, whoops, sorry. Need to get my pen out. Okay, so when it's at the top over here, we know there's a force of gravity that's going to be pulling it down. But what we should also know is there is going to be a force of tension that's pulling it down. That's the string. Okay, so it's going to look something like this. If the bucket is swinging with a speed of 5 meters per second, what is the tension at the top of the loop? Okay, so very similar to what we did last time. Sum of all force in the y is equal to mass times acceleration centripetal. Force of tension is going down, force of gravity is going down, and also acceleration centripetal is going down. So all negative. Minus force of tension, minus force of gravity, 1.2 times 10. This is going to be equal to negative mass, which is 1.2, velocity, which is 5 squared, divided by the radius, which again is a string. And they're going pretty fast, because pretty similar to the last problem. So negative force of tension minus 12 is equal to, put this in my calculator. 5 squared times 1.2 divided by 0.7. Negative 42.86. Okay, do a little bit of math. And we get negative 30.86 newtons. Okay. All right. If the bucket is swung with a constant speed, will it, if the bucket is swung with a constant speed, will it have more tension at the top or the bottom of the loop? Good question here. So we should know at the top, it's kind of the bucket kind of wants to fall down, meaning there's not going to be as much tension. While on the way back up, it needs a lot of tension to swing up. So there's going to be more tension at the bottom. Okay, hope that makes sense. Next time, I'm very excited. Oh, here's a little bit of a demonstration to talk about that. But anyway, next time I'm very excited to talk about universal gravitation. It is one of my favorite topics I get to teach about in high school. So I'm excited to share with that next time. Thanks for watching, everyone. Bye.